This second part to the Week 6 topic coverage presents a discussion on how to perform sample size determinations for proportions based on desired confidence levels and margins of error. Recall from the Part 1 video the equation for the confidence interval for sample proportions. It is p hat plus or minus the z-score for a set error rate, alpha, times the standard error of proportion. Remember that the alpha is usually, but not always, set to 0.05 and has to be split between both tails, so the z-scores are for half alpha. Also, we use the standard error and not the standard deviation. Let's work out an example with jelly beans. Assume we want to determine whether a bag of colored jelly beans has 1/3 made up of green jelly beans. So let's dump out a sample and sort it. Looks like we have 3 beans, each of green, blue, and red. We can determine the proportion of the beans being green by taking the number green, x of 3, and dividing by the sample size, n of 9. We get a rounded value of 0.333 for our estimate. Since alpha is 0.05, then the z-score for either 0.025 or 0.975 can be found either on a z-score table, an online calculator, or the Excel template. The resulting z-score is 1.96. The standard error for the proportion is calculated by multiplying the proportion estimate by its complement and dividing by the sample size. Then, take the square root of the result. In this case, we get a rounded value of 0.1571. Okay, what's that give us? A 95% confidence interval from 0.025 to 0.641. We can say that we are 95% confident that the true proportion of green jelly beans is between 2.5% to 64.1%. Does that fill you with confidence that you are getting 1/3 green jelly beans? No, me neither. So obviously a sample of 9 beans is too small. We need to take a larger sample, but how much larger? There are 2 forms of the equation of determining the minimum sample size for a proportion when trying to achieve certain performance results. The first case is for when the proportion is known, or at least suspected. The needed sample size is calculated by squaring the relevant z-score and then multiplying it to the proportion p hat and its complement q hat. Then that result is divided by the square of the margin of error, E. Recall that E, being the margin of error, is calculated by multiplying the critical z-score by the standard error for proportion. If the proportion is unknown, then the formula changes by using 0.5 for both the p hat and q hat. This is a conservative approach that will lead to the largest sample size. Sample size calculations decrease as the p hat estimate falls away from 50%. Look at this graphic showing the effect on sample size for a given p hat estimate. At 50%, n is at the maximum. The n drops to the same amount at a p hat at 25% as it does for 75%. To be safe, that is why we use a p hat of 50% when we have no idea on the true value of p. Okay, so what's going on with our jelly beans? Let's review our formula values. We have a p hat of 0.333 and an error rate of 5%, which leads to a critical z-score of 1.96. Let's now assume we want a margin of error of 0.033, or 3.3%. This means that we want our 95% confidence interval to range between 0.3 and 0.366. We now are ready to plug in our values into the sample size formula for our desired 95% confidence interval. The resulting sample size needed is 783.92. Since we can't take a fractional jelly bean, we round the answer up to 784. If you're going to round, always round up. Wow, That is a lot of jelly beans to go through just to get our desired confidence interval.